Recording in progress.
Yep, comes on everyone. Let's start off. This was the last thing that we were doing. Okay. Great. So let's write down a few steps on how do you handle this direction part. Others, do keep your cams on. Now for the magnitude, it is straightforward. Just take the flux and differentiate, you'll get the answer. If you want to find the direction, so induced EMF or current. Like I said last time, if you remember, you can always get two possibilities. In one possibility is right, it is a positive feedback loop. The system will tend to infinity, which is not possible. So you always take the other case. So simply, if you're trying to increase, I'll try to decrease you. If you're trying to decrease, I'll try to increase you. Again, understand the system has no problem with the flux. The system has a problem with changing flux. So the first step, this is what we do. Check if the flux is increasing or decreasing. Calculate flux and find d phi by dt for magnitude. Check if flux is increasing or decreasing. Step 2. Check direction of B external. If flux increases, then B induced is opposite to B external. And if flux is decreasing, B induced is in the same direction of B external. It should support. Then using right hand rule. Now, if you know the B induced direction, put your thumb along this thing, the B induced, and the fingers will give the curl of the fingers will give you the direction of the current. Curl of the fingers gives current or EMF. Clear? These are the steps. All clear with the steps? So the last class I gave you some examples. Let's see a few more.
So can you show the previous page for a second?
Let's see. We have a coil. We have a magnet, north, south. You are standing here, okay? This is important. Observer has to be given, because if I stand here, clockwise for him is anti-clockwise for him. So the direction does get messed up. So find the direction of the current as seen by the observer. Same thing if the magnet has already crossed him. So magnet is coming towards the coil. Magnet is crossing the coil. Magnet is beside the coil. What will the observers think about the current in these three cases? Let's see. So first thing, you need to ask yourself, how is the field? Now, if you look at this magnet north, south, and the coil here, this is how the field lines are. So some field lines are missing out. So if you get closer, more lines will pass through. So this is the direction of B external. Now, as it gets closer, flux is increasing. Therefore, your B induced must be opposite. Means if you put your thumb up and rotate, what will that person think? So for this person, meaning that is you, okay? So the field is coming to your space. So if you can just see, the thumb is pointing towards your face. So what will you think? Anti-clockwise. So he will see anti-clockwise. Is that fine? Now, that is one thing. That means this coil here is acting like a magnet, north, south, and it is sending the field lines this way. And that blue magnet itself is coming this way, north, south, and its field lines are this way. And if you see north and north, both are coming, this will repel. That means when you drop this magnet from a height, if you try to draw the FBD, because of this repulsion, it will have its own weight mg. It will also have some magnetic force. So we'll have an acceleration less than g. They can ask you this question also. If a magnet is dropped in front of a conducting coil, there's no current, nothing, but it slows down because it will induce a current in that direction, and both the magnetic fields will oppose each other. So it feels like it is getting repelled. Is that making sense? Now in the second case, same story, but in this case, the field lines are like this. So if you are going away, flux is decreasing. So I need to support. B external is the red one. So B induced also will be in the same direction. So B induced supports B external. So this person will think the direction is clockwise. So put your thumb into the paper and try to rotate and see. So you're seeing from the top, you're like this, you're looking from the top to the bottom. This is clockwise. And if you look at the magnet, that means the coil is behaving like a north-south magnet like this. And this blue magnet is leaving. So this is south-north. That means they will attract. So interestingly, here also the acceleration is less than g. So if you're trying to go towards the coil, it will repel you. If you try to go away from the coil, it will attract you. So either way, in both the cases, the acceleration will become less than g. Have a look at this. The repulsion part is important. So they can ask question like that also. What will happen to the acceleration if you leave it in front of a conducting coil? It will be less than g. Any doubts on this page? Clear, na, Neil? Kartika? Then the C part. This is an interesting one. North, south. Try to understand here. The field lines are going like this. There are field lines. And which way is the field? Field is upward. So if this magnet goes down, what will happen? If the magnet goes down, the field lines will decrease, right? You'll have less field lines going through this. So what is happening to the flux? Flux is decreasing. When the magnet is this close, you have a lot of field lines going through this. If the magnet goes really far, the number of lines will decrease. So flux is decreasing. So B induced will support. Like I said, I'm not interested in the flux. I'm interested in change in flux. Next moment, what will happen? Flux will change. So B induced supports B external. That means B induced also should be this way only. The most common mistake here, people mess up the direction part. When the magnet is to the side, the field lines will take a turn and go back to the south pole. So the B external is upward. So this person who is standing here, he will think it is anti-clockwise. It's towards him, right? Anti-clockwise. Yeah. Clear? Now, if I combine these two concepts, we get something more interesting. Any doubts on this, please ask me.
So at this moment, flux is constant now because it is symmetrical.
Oh,
So like even in the first cases, if the magnet is like in the middle of the coil, for that
so
instant,
according to you, B is equal to 2t, at t is equal to 1 second, velocity is 2, which is constant, right? So therefore acceleration is 0.
Nice, sir, not that.
No, it is that only. Exactly, that's what you're saying.
Uh,
Right? At this point of time, your age is something, something, something. So you don't age. You're an immortal youth being.
So what I meant is कि मतलब first the flux is
Something which changes with time. At this point, it is exactly middle, right? The next point, it is going to decrease.
Yeah, but just before that,
that I'm not interested. Interested as time goes in one direction until unless you know how to do time travel. So
it's like placing a dipole at r by root 3 now.
That's also Ishan. I'll tell you now, don't confuse yourself. You understood what was happening. Don't confuse yourself.
No,
Exam with there'll be no. What is that you didn't understand? Flux is not increasing or increasing, that you didn't understand. If I just push the magnet little here, north, south.
It was increasing and then it...
No. If you go a little forward, this field lines won't cross only through this. The flux has decreased. What is the problem?
No, but if we plot a graph of phi versus t, at this point we'll get slope is equal to 0 now. Because first it was increasing and decreased.
Perfect, na? Perfect. So sine function is there. The highest point slope is 0. Therefore, sine is constant for all angles.
Nahin.
Proved. Hence proved.
Pi by dt is constant now.
So tu wahi bol raha hu, maybe. What?
0 at that point.
What?
At this point, a d phi by dt should be 0 only now.
Itna tension mat le. We are talking about as time passes. Current will be there.
So in the previous cases, if the coil is like around the magnet, tab kya hoga?
Think about it and let me know. I will leave it to you. But you got this question, right? What I was asking. So I agree it won't be uniform, but you can't say I just kept it to the side. You don't know the distance, you don't know the angles. There are a lot of things that are changing. So you're talking only, this is the only field line. There might be a line like this, there might be a line like this. Don't make it so objective, right? It's just some conceptual question. I got your point. If it is exactly the rate of change of flux at that point, it is zero, but that function is not so linear, right? चलो तेरा happiness के लिए, let's say magnet is slightly below. Happy?
Happy, sir.
बस तुझे वही चाहिए. I gave it to you. Next thing, let's go ahead. So we have a hollow copper pipe. And you dumped a magnet inside. So magnet is released from rest. Approximately plot VT graph. Gravity is there. Or I can say, what happens to the velocity of the magnet? Approximately plot velocity time graph. Decreases. God, it is starting from rest. Decrease मतलब क्या करेगा? ऊपर जाएगा. This is nice, right? I will take you people and throw in a copper pipe and you start flying. There, I created levitation. क्या हो रहा है आज? People are creating time travel, levitation, sin x is constant. We are creating new stuff today. People are on fire today. I said it is releasing from rest. And सब कोई बोलता है speed is decreasing. और क्या करेगा? मतलब zero से और क्या करेगा? ऊपर जाएगा. Approximately. Increases and then decreases. What is happening here? Listen, this belongs to the A and B. So when the magnet is falling, just now we saw the coils behind, they attract, isn't it? If you leave the coil, they'll attract. The coils in front of you, they repel. So if you're entering a coil, you repel. The coils behind will attract. So at any point of time, if you look at the forces, this is mg, and there is a magnetic repulsion. You can call it a magnetic drag, just like viscous drag. And what will happen as you go faster, the magnetic, the change in flux will be faster. So as speed increases, the rate of change of flux will increase. And therefore the drag also will be more. They will repel and attract much stronger. Just like kind of like viscous force. I won't say it is proportional to v⁻⁴, but it does depend on velocity. The faster you go, more you induce and more repulsion or more attraction you get. And eventually, right, it will reach a terminal velocity. Eventually, F magnetic becomes equal to mg. So the speed will continue to increase. It will reach terminal velocity at infinity. This is exactly like viscous time, that time the graph would look like this, increase. It will tend to this value, but it will take infinite time to reach technically. So the speed always increases. If I ask you acceleration graph, acceleration always decreases. याद है हमने किया था ये viscosity में. AT graph, VT graph, XT graph. So that would be a good one. The speed always increases and eventually tends to a constant value. It is getting closer to that, but never reach. Acceleration will tend to zero. Clear? And what is the purpose of taking a copper pipe? If you take something made of iron or steel, there is a chance this will get attracted, right? So we want to be sure this is happening only due to magnetic induction and not due to magnetic attraction between the metal in this. It's a good one. Look at this. So this guy took a copper pipe. A thick one is better. You'll get more terminal velocity. The scale is cool. It has a panda. And then we have a... He's just trying to show the diameter. This is a neodymium magnet. These are pretty strong. You can get it on Amazon. But they're pretty brittle. If you just leave them from little far, they'll hit each other so strongly they'll break. But already these magnets are so strong. I had one. I brought this thing. Literally, you have to put so much force. It doesn't come out only. And there's a high chance your fingers will get trapped between. It'll pinch your skin. So you have to be quite careful if you buy one. Anyway, so that's almost, I think, 2 centimeter radius. And there, he's trying to show you, Deko. If you put like this, there is no attraction because it is copper. Now, when you leave it, see what happens. Can you see? Aram se it goes. So here the magnet and this thing is so strong, you are getting terminal velocity. And we know other friction and all stuff is there. There. Takes time. You can do this. You can buy this copper pipe and you can get a magnet from Amazon. It works. It works pretty well. There you can see, literally it is gliding. You can even lift it also. That's the attraction. So he was trying to show the time. There, this you can see more clearly. You can see how it's floating. So there. So this is not an illusion, and I'm not bluffing. It does happen. That means you're going to put 4 magnets, 2 to your hand, 2 to your legs, and throw you into the copper web, you'll float. Clear with this? Let's see one more like this. See, all these are like theoretical questions. Suppose if you have a battery resistance and a coil is there with a switch. You keep one more conducting coil here. Now, if the switch is closed, what happens between them? They repel, they attract, nothing happens, depends on the direction of current. So this is like a coil 1, which has a battery and resistor. Coil 2 has no battery, just a coil. Now you can say it has some resistance. It has a coil, that's it, it is a wire. What happens when switch is closed? If I keep the same pole, I can never. Then you can do that. But then उसमें induction कुछ नहीं है ना. You're just using magnetic repulsion. What happens here? अरे God, velocity is decreasing. Velocity is increasing, but it's not. Acceleration decreasing मतलब क्या? If rate is also increasing मतलब क्या? तो सोचो. Why will velocity tend to a constant value? V is increasing and acceleration is also increasing. Then why will velocity tend to a constant value? It will blow off to infinity. Think a little. Examine who will come and tell you all these things. Kya the answer? Repel, like after switch is closed or just switch is closed. वही बोल रहा ना, switch is being closed, switch touch करेगा, switch will fly. इसने switch closed. बस exam mains and bits exam they're not going to give you so much details, right? Yeah, my room का lighting is so bad. Anyway, see what happens. The moment you close the coil, there will be some current in the coil, meaning the current will go from 0 to I. So this will produce some magnetic field lines. So this coil 2, so see the point is, what will the coil 2 think? So coil 2 will feel flux suddenly increased. Initially had no flux. So coil 2 feels flux increased. हाँ, उसके बाद constant हो जाएगा and all, that is fine. At that instant, flux increased. So this will generate a counter field to repel. So this will act like a magnet north-south, and this will act like a magnet north-south. And therefore the repel. What if the current was in the other direction? It doesn't matter. If the current was in the other direction, then this would act like north-south, and this would act like south-north, isn't it? It will still repel, right? So it doesn't matter about the direction of the current. If the field lines are going like this, it will try to generate a flux to oppose this. So B induced will be in this direction. So it will be south-north and south-north. They'll still repel. So it doesn't matter how you close the switch, like current goes clockwise, anti-clockwise, they'll always repel. Clear? Great. Let's say a question. What was the last question number? This is not 1, this is 3 already. Great. Let's see our question. We have a coil here. You can treat it as almost a circular coil. Small space is there. This radius is 2a. This radius is a. This resistance is r, and this resistance is 2r. The magnetic field in the region is B naught into T, and the magnetic field in the region is B naught into T. In the second case, the same coils, but this time it is twisted. You're getting the coil twisted. This is R, this is 2R, everything same. Find the current in the system. This is 2A and this is A. Find current. I want magnitude and direction. Yeah, that is not how you give the answer. I want you to find the current in the loop. What will you do with what you give? Find the current in the loop. Where is the resistance? Nothing is there. You just mentioned something else. Should I help you with one? Try. I'll give you a minute. Basically, you can treat each coil as independent, but they're actually not independent. So start from there. See how much EMF is induced in each coil. See, the first one, So in the first coil here, the flux phi1 will be B naught into T into 4 pi A square. So EMF will be 4 B naught pi A square. This flux 2 will be B naught T into pi A square. EMF in the second coil would be B naught pi A square. Now, what is happening in both the cases? Flux is increasing. Therefore, B induced will be opposite to this. So B induced is this way. So the batteries would be like this. This would be E1 and this would be E2. Agreed? They will try to push the current in the which way? Anti-clockwise direction. Now, when you take the current like this, I, actually in this case, both the batteries are supporting each other. So I is equal to E1 plus E2 by 3R. Make sense? But the same thing when you try to do the next question, because you got twisted there, the story is still the same. They will, so each loop is trying to push the current in the anti-clockwise direction. But because of the twist in the middle, this is acting like E2. Now see what happens. This is the current I, this current is going opposite to this. That's it. That is the only difference. In the B part, the current I would be E1 minus E2 by 3R. Resistance always adds up. So in the second case, the two coils will have an EMF in the opposite direction, so they will fight. Clear? Resistance always adds up. Ishan, you can say like that also. So you can just treat them as two independent loops and finish it off. Is this clear, everyone? Easy? Let's see one more. Turn in the page. Udayan, Rehan, Vidyut, Yasha. Great. We have a conducting rhombus. This is theta. This is a rhombus of side L. Basically, all sides are equal. So this is O, this is A, this is B, and this is C. So someone caught this point and started pulling with constant speed U. And inside we have a magnetic field B. B is constant. So we have a constant magnetic field. Okay. So the point B is pulled with constant speed U. Find the EMF of the loop as function of theta. Meaning when you pull this, what will happen to the shape? After some time, this will become like this, right? And if you keep pulling, this is what is happening here. So what is changing here? Like I said, whenever you want to change flux, you can change B, you can change area, you can change theta. So in the previous problem, B was changing with time. In this case, area is changing. Let's get this. Find the EMF as function of theta. Theta is that half angle. How do we approach this? Idea is the same. Step 1, find the flux as function of theta. Step 2, differentiate. 2 BL sine theta. How the hell did you get that? Nope, that's not the answer. Try. I'll give you a minute. Let's see. So this thing, right? This is L 90. This is L sine theta, and this is L cos theta. So at any point, the area would be 4 times half into L sine theta, L cos theta. Agreed? So there are 4 triangles there. So that would be L square sine 2 theta. 2 sine theta cos theta, that becomes sine theta. Then flux will be magnetic field into area. Angle is anyway 0 here. Be careful, theta is the angle between B bar and A bar. It is not this theta. Don't write cos theta here. BA cos 90, that is. And this is B into L square sine 2 theta. Itna tak sab great hai. So EMF will be minus d phi by dt. You end up with BL square 2 times cos 2 theta d theta by dt. How do you find d theta by dt? Now, if you look at this distance here, x, that is nothing but 2 times L cos theta. If I differentiate on both sides, dx by dt, that will give you 2L minus sine theta d theta by dt. What is x? X is the coordinate of point B, isn't it? So rate of change of x is nothing but the speed. So this is u is equal to minus 2L sine theta d theta by dt. There, from here you got d theta by dt is equal to minus u by 2L sine theta. Is that making sense? The point B ka coordinate is how much? 2L sine 2L cos theta. So the rate of change of 2L cos theta must be the speed of B. Substitute here. So therefore EMF will be 2BL square cos 2 theta, and this guy would be minus u by 2L sine theta. So EMF will be 2BUL 2 जाएगा cos 2 theta by sine theta. That is your EMF as function of theta. Now, if I can simplify this a bit, BUL, I can write cos 2 theta as 1 minus 2 sine square theta by 2. So this is 1 by sine theta minus 2 sine theta, right? So this thing kind of looks like 1 by x minus some 2x type of function. So if they can ask you to plot the graph also, so you can put then theta is equal to 90, And then you can try to plot this graph. You can clearly see this will come maximum value when theta is 45. You can do maximum minimum also and check. They can answer that question also. Find the angle when the EMF induced is maximum at 45 degrees in this case. Clear? Next one. Any doubts on this?
Just
So this part is the mechanics part.
Just need this at 2 minutes before going to the
Yeah.
next question.
You know, how can I play this question another way? We can put a rod like this. And we'll say we can drag this with u theta, and this is theta, and we'll see here is the magnetic field B. Remember that question? We did that in NLM. We will see this later on in another way. You could have done the same thing with this question also. Idea is the same. d phi by dt. That will come automatically the minus sign, right? Cos theta ka differential hai God. You have one weird doubt. You didn't have a problem with EMF, flux, induction. Nah? Next one. BA cos, BA cos 0, my mistake. You're right, Anusha. Next one. Our favorite, spiral. N turns, tightly bound. So you take this point here and this point here. So maybe you'll connect some kind of a resistor kind of thing here. B not T. Inner radius is A, outer radius is small b. Find EMF in the loop. What are the steps? At a distance x, take a thin thickness dx. The number of turns in dx will be n by b minus a into dx. So flux in that coil, okay? Flux in that one coil, that flux in that coil of radius x, I'll just call it flux coil, would be total number of turns is n by b minus a into dx into magnetic field is b naught t into area is pi x square. Now flux on the spiral is integrate all these coils, add all the flux of all the coils here. Now be careful here, when you're integrating with x, so time is constant. You are calculating flux as a function of x. So this is n b naught pi t by b minus a integral x square dx from a to b. So for a given time, you're calculating the flux as function of x here. So this would be n b naught pi t b cube minus a cube by 3 times b minus a. So there you got the flux as function of time t. Now EMF will be d phi by dt. I'm just getting the magnitude. And b naught pi b cube minus a cube. You can simplify it further, but okay. Clear? Any doubts on this spiral? This is the third time you're seeing. We saw once in magnetic moment, then we saw in magnetic field. You're saying this is the third time. Turn in the page. This is an AC generator. We have a coil here. This is rotating with omega. So this would be your area vector. The magnetic field is constant. In real life, we do the reverse. We keep area vector constant and we rotate the magnets. Remember last time I showed you that simulation, water was falling, it was rotating. And in this process, so basically in this case, you're changing theta. So find EMF induced in the coil. Radius r. Find the EMF induced in the coil. And find the charge flown when the coil rotates 180 degrees. Initially, theta is 0. How much charge will pass through the coil? Per half revolution. The second one is what is more important. Let's see. This was straightforward. But I'm more interested in the second part.
फिर वो theta जो है, is it like ऐसे कि ऐसे?
Doesn't, I know omega क्या दिख रहे हो ना, ऐसा ले लेना.
नहीं,
So basically the theta is omega t. That omega is changing theta. बस वही था. So flux will be B A number of turns into cos theta. So that would be N B A cos omega t. Differentiate. So EMF will be minus d phi by dt. that would be NBA omega sine omega t. So this is the power supply that we get. Right. So this number will become 220 root 2 volts. This omega becomes 2 pi f 50 hertz. So this is fine. What about the charge flown? Now we can see here EMF is d phi by dt divided by resistance on both the sides. So this is 1 by R d phi by dt. This becomes current. So I into dt is equal to d phi by R. So if I integrate on both sides, I get charge flown is equal to change in flux by resistance. You should remember this formula, straightforward.
Resistance was given.
Come again.
Resistance was not given.
What?
You're saying resistance was not given.
Resistance देना चाहिए था. Taken a resistance is there. Let's say radius is A. R is the resistance. I should give you the resistance. You're right. But like I said, the formula is more important, so keep that in mind. So this R here is the resistance. So I'm not interested in how the flux is changing. Simply change in flux by resistance. So in our case, change in flux will be number of turns into B into area into 2 times. Initially it is BA, finally it is minus BA. Na? Maybe I'll write that. N into BA, initial final minus of minus N into BA. I'm just taking the magnitude. Final flux minus initial flux by resistance. Clear? That would be a straightforward mains level question or a bits one. In this, I can do something else. I can create another type of AC generator. All clear with this? Easy one?
Answer the previous. Can you show the previous?
Why is your voice so weird? It is not coming properly. I can hear only bits and pieces of it. Maybe get a better mic or maybe I don't know. नहीं तो message कर लेना. I think there's an issue with your mic. Clear? Clear, na? Then, so we have a magnetic field B here. Now you took a coil, semicircular coil. This is the hinge in the center. And this coil is rotating like this with omega. Meaning next moment it will become like this. Then it will become like this. Then it will become like this. Then it would go inside. Then it will start coming out. So I hope you're getting how it is. The coil is turning and coming out. So it's like this. So radius is A. Magnetic field is B. So this coil rotates with omega in the plane. Plot EMF versus time. Take anti-clockwise as positive direction. If the current flows anti-clockwise, take that as positive. Hmm. Any answers? What is changing again here? Doesn't the question need to keep asking what is changing? Hmm. E is that is a catch, Lakshika. It is not constant. It looks like constant. There's a small catch. So if you see at any point of time, this guy is going like this. So this is your angle theta. You're interested in only this area, isn't it? You're only interested in that area. And we know area of a sector is theta r square by 2. Theta a square by 2. I hope you know that. For 2 pi area is pi a square for theta, what it is. You can use unitary method. So flux will be theta a square by 2 into magnetic field. So EMF will be, I'll just get the magnitude from here. That will be a square b by 2 d theta by dt. So magnitude is constant. That is what you should say. You should not say EMF is constant. A square b omega by 2. So what is the direction here? Now you need to understand when it is entering, while entering, the flux is increasing. So B induced will oppose. So B induced is this way. Therefore, the current is, put your thumb board in this thing, anti-clockwise. Now the same coil, after 180 degrees, it starts coming out. It's coming out like this. So now in this case, the flux is decreasing. Magnitude is constant. Now B induced will support the system. So B induced is this way. Current is clockwise. So when you try to plot the graph, most people will think the magnitude is fine, but the direction keeps changing. So for half revolution, it will be positive, anti-clockwise initially. That's why I said anti-clockwise is positive. Then it goes negative, then it goes positive, then it goes negative. It's a discontinuous function. Every half revolution, the direction keeps changing. Clear? Right, I know. So this is also an alternating current. We will define it later on. Alternating current meaning it should keep changing the direction periodically. Is this clear, everyone? That's it. The trap in this is the direction is changing. Magnitude is fine.
You can start from bottom or top.
I gave like this initially. You can start however you want to draw.
Like
I gave na यहाँ पे anti-clockwise is positive chord.
the flux is increasing, then EMF is in the opposite direction. Minus theta by 8.
Okay. Then
I think it should start from the bottom.
what starts from the bottom?
The graph.
Why?
You got the flipped graph.
I'm not understanding what you're saying. Initially, flux is increasing. So B induced will be which way? Out of the plane. So current initially will be anti-clockwise. Yes? No? And it is given anti-clockwise as positive. So what's the problem exactly? Or did I do some mistake here? Next one. Think about it. Let me know if you're still confused. Clear na everyone direction but initially it is anti-clockwise, the starting part. While you're entering it is anti-clockwise, while coming out it is clockwise. Next one. Let's see how many of you will get this one. This is a good one. It's a serial killer. So we have a circular coil here. The magnetic field is B naught T. The radius is A. It's a circular wire with uniform resistance R. So this point is A here. This point is B here. This part is angle theta. Find the potential difference VA minus VB. A and B are 2 points on the circular loop. Find the potential difference between A and B. Think, I'll give you one. It's a good one. Let's see. Is there any catch? Okay, let's see. First thing. The Faraday's law, right? The problem with the Faraday's law, right? It gives you the EMF. And like I told you, Faraday did this completely experimentally. He has no clue why this is coming, right? So Faraday's law gives EMF in the loop, but does not give us the distribution of EMF in the loop. So I don't know which part is creating how much EMF. Now, tell me one thing, is the EMF and potential difference same? So flux we know is B naught T into pi A square. So EMF will be B naught pi A square. Flux is increasing. So current E will be E by R. Flux is increasing, I need to oppose it. So it should be outward. So this is anti-clockwise. Anti-clockwise. Okay. So the catch here is, now because of symmetry here, I can argue whatever EMF you're getting, like, till now what we're doing is you're putting a battery. But in reality, every segment is generating EMF. Due to symmetry, we can say EMF is uniformly distributed. That means each segment will act like a EMF with its own internal resistance. This segment will act like an internal with its own resistance. So every segment will have its own battery and own resistance. Now in this, if you take point A here and point B here, That means for this segment AB, I can say there is a one battery here and there is one resistance here. This is B and this is A. And this is current I, which is E by R. So because it is theta length, it will also have a contribution of how much EMF? Theta by 2 pi into EMF. How much will be the resistance? Theta by 2 pi into capital R. Agreed? So that small segment will have an EMF of this much, and that small segment will have a resistance of this much. Now applying Kirchhoff law, you're going from B to A. So VB minus I into theta R by 2 pi plus EMF theta E by 2 pi. Then you reach VA. So we get VA minus VB is equal to theta by 2 pi E minus IR. But I already know I is E by R, 0. Independent of theta, you'll get 0. That's what I'm saying. Don't get confused between EMF and potential difference. The EMF is theta by 2 pi into V. I contribute this much, but my own resistance will also eat away that much potential, isn't it? Whatever EMF I'm generating, my own internal resistance is eating away that potential. Potential difference is completely different from EMF. For example, this question say, if this is R and battery E, if I put the wire like this, what is the potential difference and what is the EMF? EMF is E, potential difference is 0. There is no potential only. Basically, whatever EMF I generated, my own resistance ate away that potential. The potential difference is 0. Is this making sense, everyone? Independent of theta, you'll get 0. The main catch, wire should be uniform. And the shape should be uniform. You give me some weird shape like this, then I can't argue and say like, boss, every segment will be equal EMF. Is this clear, everyone? Let me give you another variation of this, but try to understand this first. If the question was how much EMF AB is contributing this much, what is the potential difference A and B? The question has changed. Clear? Let's see one more like this. Turn the page. Yasha, Vartika, Palaksh, Aryan, Ali, Adrit. Perfect. Next one. Equilateral triangle. So this logic, right, that the EMF is equally distributed, you can say for regular polygons. Equilateral triangle, side A, this resistance is 2R, this resistance is 2R, this is R. Now understand, EMF has nothing to do with the resistance, it doesn't care, it will only see the area of the loop and all that stuff. So this flux is B not T. This is A and this is B. Find VA minus VB. This is the kind of question you can get. Both are kind of related. Let's get this. show you. Okay, let's see. You goofed up, yeah? I'm not sure. I might be right only. Let's see. So first thing, area. It's an equilateral triangle. So half into base into height. So flux is equal to B naught T into area. So EMF will be B naught into area. Direction, flux is increasing. So I need to oppose this. So my B induced should be this way. So this is anti-clockwise. Now, because due to symmetry, now you can argue again. If this, you give me some scalene triangle, I can't say anything. Due to symmetry, EMF will be equally distributed. So this is the resistance. The batteries will be anti-clockwise. Battery. This is how the circuit would look. E by 3, 2R, R, E by 3, E by 3, and 2R. The current in the circuit I will be E by 5R. This is your current. You want to go from A to B. So VA minus I into R, you're going in the direction of the current. You're going through the battery, negative to positive, so plus E by 3, and you reached B. So VA minus VB is equal to IR minus E by 3. IR is E by 5, so minus 2 E by 15. Be careful with the sign. There will be two options, 2E by 15 plus 2E by 15. Magnitude you might still get, you might have goofed up something. And E ka value is B naught A and A ka value is root 3 A square by 4. So you can substitute all that stuff. There, in this case, it won't be 0. If you had got 2R, 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 all would have been 2R, now would have got 0 again. So you can always argue that the EMF will distribute uniformly if you have a symmetrical shape. It has nothing to do with resistance. But if you mess up the resistance, you can create potential difference. So don't get confused between EMF and potential difference. Both are completely different things. Once in a while, they become equal. Clear? So this is another good model, that the distribution of EMF part. And be careful with the directions. Huh? See, once you get the EMF, it becomes a current electricity equation. Next one, turn in the page. Motional EMF. Medical people call it emotional EMF. I tell them that only. When you become emotionally very strong, you generate a lot of EMF. And if you seriously explain them, they'll think it is real also. That is one thing. Medical people, you can talk any shit and you can tell them it's a concept. They'll think, oh, now what is this thing? See? If a conducting rod is moved in a magnetic field, we observe a potential difference across the ends. Now, why is this happening? First, let's take a simple case. So we got a rod here. Let's say this is going with velocity v, and let's say the magnetic field is b. So inside you have a lot of free electrons. So if you look at this electron, the force on them, this is v, magnetic field is b, v cross b is upward. But remember, electron is a negative charge, so force will be downward. So basically, these are free electrons. So whatever I'm saying won't work for insulators. So now because of this, what will happen? So when I take this rod and start accelerating with going with speed v in the magnetic field b, the electrons will start accumulating here and this will start becoming positive. So these guys create a field. So E is the electric field due to induced charges. Clear? Now the electrons will keep moving. At one point, the electric force and the magnetic force will become equal. You reach a steady state. So in steady state, you have magnetic force, EBB. We have electric force, EE. They both become equal. This is the negative terminal and this is your positive terminal. So from here, we get electric field is equal to V into B. So this rod starts acting like a battery whose EMF is given by BLV. So we know potential difference VA, V plus minus V minus is equal to minus E dot dl. That would be BL into V. So this starts acting like a battery of BLV. So the positive charges will act like a positive terminal and this will be the negative terminal. Now, how do you find the direction of the terminals? So this is what we do. Now EMF is straightforward, BLV, that though you can remember that. I'll show you even a more better case. For finding direction, this is what I do. Assume finding direction of the terminals or finding positive terminals. How do you know which side of the rod is a positive terminal? Assume a plus Q charge and see the direction of magnetic force. That though you know how to calculate. QV cross P. So whichever side the positive charge goes is the positive terminal. Because that is where all the positive charges will accumulate. So that will start acting like a positive terminal. That will be the positive terminal. Automatically the other side electrons will accumulate, so that will be the negative terminal. Making sense? So let me give you some examples. Can you tell me the directions? I'll write a better variation of this BLV, but let's see the direction part. Suppose if you have a rod like this, rod is going like this, and this is the magnetic field. Which side is positive, which side is negative? Figure it out. This is going with V and this is B. This is a current wire I and this rod is going like this. So for the first one, what we do? Assume a positive charge Q. This is going with V cross B. So this side is the force. So this is the positive terminal. This is the negative terminal. Make sense? Here, assume a positive charge Q. This is the velocity. B is inside. So V cross B. force is this way, meaning positive charge will accumulate here, negative charge will accumulate here. You just assume there's a positive charge, see whichever way it goes is a positive terminal. What about this guy? This current will produce a magnetic field into the plane. So assume a positive charge, and this is V cross B. So force would be this way. This would be the positive terminal, this would be the negative terminal. Directions are clear? The directions are important.
Could you go to the
There.
previous slide?
Mm-hmm. $36. Yep. Take a break. Come back with 7.5. Any doubts so far?
Can you say the next page?
Mm-hmm. Chalo, come back in 10 minutes.
So, so
Next thing. Chalo, camps on everyone. Kush, you wanted to say something?
Sir, I'll ask it after
You want-
class.
Okay. Now, what happens if this rod is not going in a perpendicular to this thing? Let's say if it has a velocity b, theta b and length L. So I can split this into two parts. This is v cos theta b plus this is v sine theta into b. Now again the same logic. If I put a plus q charge here and see which way it goes, this terminal will be positive, this terminal will be negative. So this guy will act like a battery like this, which is BLV cos theta. This guy, if you put a positive charge here, QV cross B, this side will be positive, this side will be negative. So if the width of the plate is D, there is a thickness, then you can say this acts like a battery of EMF BD. But generally we take thin rods. D will tend to 0. So we ignore this. So generally whenever say EMF of the rod, we will say it is BLV where B, L and V are mutually perpendicular. That is the general catch. So if any one of them is parallel to the other, you won't get any EMF. That will become this case. Clear? So that velocity should be perpendicular to length and perpendicular to B. Now, if I make it even more generalized, sometimes, it can happen. They will give you field in some direction, wire is in some direction. So let's say if you have some random loop like this is DL bar, this is V bar, and let's say B bar is in some direction, maybe 3-dimensional. Now in steady state, eventually the charges will accumulate. The magnetic force plus the electric force, the total sum will be 0. So this will be EV cross B plus EE equal to 0. So from there we get electric field E is equal to V cross B. So if this is real bar, now let's say the electric field will come in some direction, we don't know. So this will be E parallel and this will be E perpendicular. And we know the potential difference comes only because of the EMF, the E parallel. So E parallel is responsible for EMF along DL. E dot DL, no? So D small d EMF induced would be E parallel DL, which is minus V cross B. And that becomes, so this is nothing but E cos theta. DL, that becomes E bar dot DL. Or you could have written integral E dot DL, that also would have worked out. Minus V cross B dot DL. So this is your final formula. So the EMF induced in the rod is integral minus DL bar dot product of V cross B bar. Meaning, let's say someone gives you like this velocity of the rod is 3I plus 4J minus 2K. Magnetic field is I plus J plus K. Now, if you give me in 3-dimensional, it is very difficult to figure out. This is still in 2-dimensional, so you are able to see and tell the answers. If you give me in 3-dimensional, this is your formula. So this is a simpler version, BLB. This is fine at an angle, and this, if they really try to play in 3 dimensions. Clear? Now, next thing, our favorite one. Suppose if you have some random curve, which is going with V, and we have a magnetic field B, what do we do? We take the projected length. Why does the projected length work? Simple idea here. If you make a full closed loop, if you give me a random curve, right? Plus, if I give this line, you will get a closed loop, isn't it? So flux of that loop is constant. Magnetic field is not changing. And therefore, EMF in the loop is 0. That means whatever EMF the curve is generating, the straight line also must generate the same EMF, isn't it? Therefore, I can simply replace this with a rod. Let's say if it is like this. So just join the ends, right? You can replace this with a rod like this, which is going with V, and you can just solve. So EMF of a curve is BLB. I'll just keep it straight here. नहीं तो वापस वो एंगल सब लेना पड़ेगा. So you can just replace this with a rod here. So you can replace this with a rod of AB. B into length AB into V. So LAB is your projected length. There. This is the 4th time. The projected length. Example. If they give you something like this, a semicircle, magnetic field B and going with V, I can replace this with a rod of 2R. I can treat this as a battery B into length into velocity. Where this will act like a positive terminal, this is like a negative terminal. Clear? Again, like I said, B must be uniform. So great. So we got Faraday's law, we got motional EMF, we got 2 of them. It's like exactly, does it mean there are 2 kinds of EMFs? What are these 2 concepts exactly? So when I solve the problem, should I take Faraday's law also? Should I take motional EMF also? What are these 2 things actually talking about? So the catch is this. First thing, the Faraday's law is completely experimental. Like I said, Faraday didn't have an idea why it is working. He simply said, I did this experiment and I'm observing this every time. Motional EMF is theoretically, we have derived it literally on a page. We wrote equations and we derived it. So we are actually talking about the same thing. So Faraday's law is experimental. Just that he doesn't know what was happening. And motional EMF is theoretical, explaining the same thing. Something this happened before also. Do you remember which concept is that? Anyone remembers?
Ampere's law and
Ampere's law.
Biot-Savart law.
नहीं रे, दोनों को रिलेशन ही नहीं है. Yeah, right side. Pressure and bind force, remember? Archimedes didn't know why bind force was coming, but it works. The reason why bind force comes is because of the difference in pressure between the lower and the upper surfaces. That is the reason whenever we drew an FBD in fluid mechanics, if we use pressure, we don't talk about bind force. And we talk about buoyant force, we don't talk about pressure. Do you remember that? This is similar to pressure and buoyant force. Buoyant force was an experimental quantity, pressure is a theoretical one. Therefore, if we use Faraday's law, don't even talk about motional EMF. You cannot say both are there. If we use Faraday's law, don't mention motional EMF. Now, which is important? Nothing like that. Both are important because both have a certain kind of restrictions. I'll tell you what are those. EMF and vice versa. If you say motional EMF, don't talk about Faraday's law. Be very careful with that. Don't use both. It's a blunder. The issue is which one is better. Faraday's law is only valid for loops because he derived it for a loop. And you know why it is a loop? The thing is this way. Faraday, what he observed was actually current, isn't it? Faraday observed the current and then he said, yeah, current hai, matlab there's an EMF, and then from there he argued there's an EMF induced. Now, if you don't make a loop, circuit is not completed, you'll never get a current. You getting the problem? So that is a problem. Faraday's law works for loops. But motional EMF says, boss, even without a loop, I can generate EMF. But the problem is, it should be moving. Just put a rod here, and if you change magnetic field, you can't find the EMF, right? So motional EMF restriction is this, it should be in motion. So you need to know both the techniques. Sometimes this will work, sometimes that will work. Both are valid, but you won't be able to use it. If I give you a rod, Faraday's law is not valid, meaning you can't use Faraday's law to figure out anything. So motional EMF works for objects in motion. So you need to know both the techniques. Let me show an example where sometimes both will work. But this is one important idea. Keep this in mind. So some people will use Faraday's law and motional EMF both at the same time, and they'll get double battery there. It's like having 1 lakh in the bank account. You write a check for 1 lakh. Now you have 1 lakh ka check and 1 lakh in the bank account. So you have 2 lakhs. Money doubled. Interesting idea, right? Money double scheme. Point by A, if I use the check, forget about the money in the bank. If you want money in the bank, don't talk about the check. You don't have 2 lakhs. That way. It is the same money you're talking about. Let me show you an example. Turn in the page. Let's say we have a resistor here. We have a rod here. This is a top view. This is the magnetic field. This is the length L. So let's say this rod is going with V. So let this distance be X. So I'm using Faraday's law. So Faraday will say the flux is magnetic field into length into X. The EMF will be BL into V. And here the area is increasing. Since area is increasing, flux is increasing, B induced will oppose, so it will be this way. Therefore, the EMF is anti-clockwise. So he will say, now Faraday has no idea where is the battery. He will simply say there is a current I flowing like this. And he will say I is equal to BLP by R. That means if you try to apply Kirchhoff's loop law, it will not work. Because what is Kirchhoff's loop law definition? The sum of the potential difference across the elements in a loop is 0. Right? But here, if you see suddenly, there is no element here, but there is an EMF. If you include the EMF induced also, then Kirchhoff's law will work. But if you go strictly by the definition, it simply says EMF across the elements, and there is no element here. There is only resistor and a rod. This is what Faraday's will say. The same question, if you tell motional EMF to solve, this is going with V. There is a magnetic field B. So the motional EMF will say this rod will start acting like a battery, which is BLV. And it will say the current I is BLV by R. Both of them will get the same answer. This is using motional EMF. Clear? So if you use motional EMF, don't talk about flux. If you want to talk about flux, don't talk about motional EMF. End of the day, both you will see the same answer. But when things are moving, motional EMF gives you little more information. Like where is the EMF also? If you ask Faraday, boss, where is the EMF? Is it near the resistor? Is it in this wire? This wire? This wire will say, I have no idea. I can tell you only EMF in the loop. But motion EMF will say, because the rod is moving, all the battery is only on the rod, remaining wires don't have any EMF. Hope you're getting the difference. You get little more information in motion EMF. It tells you the position of EMF. Let's see a question. You will understand. I'll give you a question which will make this even more clear. Any doubts on this concept? So we have magnetic field on the left-hand side. We have a loop. It's a square loop, side L. This loop is coming out with speed V. This is resistance R, resistance R, resistance R, resistance R. This is A, B, C, and D. So left side there's a magnetic field, right side there's no magnetic field, B is 0. Find VA minus VB and VC minus VD. This is a good question, right? Find the potential difference between AB and CD. Looks right, Ishan. Let's see. First thing, see. Let's say we'll use Faraday's law and try to solve. See what happens. Let this distance be x. Let this length be L. So we are only interested in this part of the area. So flux will be B into L into X. So EMF will be B into L into V. So current will be BLV by 4R. Itna tak acha hai. I can even find the direction. Flux is decreasing, so B induced will support. So downward. So current will flow clockwise. Clear? Now the problem here is we are not sure how is the EMF distributed. And there's no symmetry also. I can't even say like, yeah, all will be equal. So Faraday's law will give you the current and done. Story kata. Matlab, Faraday's law will say like, boss, I have no idea how to distribute the EMF. You're getting the limitation. Now, if I use motional EMF, the motional EMF will say this is A, B, C, and D. For this rod AB, the velocity V this way, magnetic field is B this way. So this guy acts like a battery, BLV. For the rod BC, and here length is parallel to B bar, V bar. So EMF is 0. So EMF of BC is 0. It doesn't contribute anything. Same logic for D into A is also 0. And for CD, there's no magnetic field only. Therefore, EMF of CD is also 0. That means all the EMF that was being generated was actually generated only by AB. Are you getting it? Now, Faraday didn't know this. Faraday simply said, here, loop mein EMF is this, which is not wrong, but that was little this way. So all the battery was present was only in this place, AB. The current in the circuit, I is equal to BLV by 4R. So you'll get the same current. Up to current, there is no issue. Are you getting the difference? Now, if I want to find VA minus VB, VA plus BLV minus I into R, current is flowing this way, is equal to VB. So we get VA minus VB. I will just write this as E, okay? So thoda simplified ho jayega, E by 4R. So that would be minus 3E by 4. Whereas VC minus VD, VC minus IR is equal to VD. We get VC minus VD is equal to E by 4. Is that clear, everyone? That was a catch. In the rod CD, there is no battery. In the rod AB, there is a battery. So that EMF, which was Faraday was saying, it is true, but all that EMF is only there on AB rod. Is this clear, everyone? Do have a look at this. Clear, na, Aditya? Adrit, got the idea there? Yeah. You're right, Ishan. Clear? Any doubts? Anusha? Clear with this? Rehan? Vartika? Malika? Let's see. Next one. We have a V-shaped conducting rail. Stop view. Smooth, fixed, V-shaped rails. This angle is theta. magnetic field is B. You have a rod, long rod. For this rod, resistance per unit length is lambda ohm per meter. Mass of the rod is M. Right. So initially the rod is at the starting point. So T0, you are here. Getting it, and someone kicked it with velocity V0. So the rod started sliding on the floor. This is a top view, so there's no gravity. The rod is given speed V0. It slides on the rails. As shown. So this is after time t. After time t, it has moved some distance. Find the velocity as function of x. So at this instant, this guy will have some speed v. And velocity as function of x. I can even ask you find the maximum distance it travels. Question is clear? I mean, like find the position where the rod stops. I hope you're getting what is the catch here. When the rod is here, how is the current flowing? Like this, right? Current is only flowing here. When the rod is here, current is flowing like here. So what is happening here? Resistance is increasing now. I hope you notice that. When it is here, this is the resistance. When it is here, this is the resistance. The resistance is becoming bigger and bigger. Right? Anyone didn't get the diagram, please ask me. Show the circuit. Try, leave a minute more. Just to give you an idea, I'll just draw the circuit you try. So after some time t, this was the diagram. Now understand, we are only interested in this green part of the rod. The outside rod is useless because current only flows within this part. This section is just hanging outside. this is theta by 2, theta by 2. So this length will be 2x tan theta by 2. And the magnetic field is B. So this will act like a battery like this. So whose EMF will be B, length is 2x tan theta by 2, and the velocity is V at that instant. Velocity is also not constant. And what is the distance of the circuit? The distance of the circuit is lambda into 2x tan theta by 2. Interestingly, current E by R comes out to be BV by lambda, constant. That is the best part. You get a constant current in the circuit. Now what? Who is slowing down this rod then? Someone has to slow it down. Why? When the resistor is, when the current is flowing through the resistor, it is producing heat. So someone must be giving this energy. You must be getting energy from somewhere. Current I is flowing like this. Yep. So now, if you look at that green rod and if you try to draw an FPD, we have a current I and we have a magnetic field B. ILB is acting backward. That guy is decelerating. So ILB is equal to MA. Current is constant. Length will be 2x tan theta by 2. Magnetic field is constant. This is mass into velocity is minus v dv by dx. Minus because it's decelerating. Shift that side.
The I is not constant.
I is constant, right?
तो
I
V
constant
change
नहीं, वो भी v change हो रहा है ना. BV by lambda. So v cancel हो गया luckily. That is even better. So b square by 2b square by m lambda tan theta by 2 x dx will be minus v dv. Integral 0 to x v to some v dash.
तो सब minus dv होगा ना?
Minus v
तो
cancel हो
minus-
गया ना. Yeah, you're right. So yep, we're done. So v minus v naught is equal to minus 2b square by 2 also will cancel off now. B square x square by 2 will cancel by m lambda tan theta by 2. If they ask you when will it stop, you'll put v is equal to 0. From there, you'll get x also, the maximum distance traveled. If someone asks you what is the total heat produced, what will you do? If I ask you what is the total heat produced,
The decrease in kinetic energy should be the heat.
something else. If you want heat produced as a function of time t, that will be a little painful. That would be I square r dt, 0 to time till it stops. But if you want total heat, that would be very easy. Half m v naught square. Isn't it? All the finally the kinetic energy stopped. Where did all this energy go? There's no other place. Everything has become current and become heat. All the kinetic energy of the rod becomes complete heat. But if I ask you find the heat produced in 1 second, that's a painful thing. You have to integrate. I भी change हो रहा है, R भी change हो रहा है. Time के साथ. It's a painful integration. Clear with this? Let's see one more like this. It's a good one. It's a variable resistance. We have a resistor. We have vertical conducting rails and we have a rod. Mass M, length L. This length is L, okay? It is just touching. I gave little space. Gravity is there. Magnetic field is there. These are vertical conducting rails. Smooth. The rod is released from rest. In the second case, you took the same question, but this time you kept a capacitor. The same rod, mass M, length L, magnetic field B. Find the velocity after time t. These are, you're seeing the front view. Gravity is there. So that means here the gravity will pull you down. Because of that, you'll gain speed. Because you gain speed, you'll get you'll act like a battery. If you act like a battery, you'll get a current. If you get a current, you'll get an ILB. If you get an ILB, you'll mess up the acceleration. That means you'll mess up your speed, you'll mess up your EMF, you'll mess up your current. So this function is killing itself. Let's get this. A simple question will be find the terminal velocity for the first case. Let's get that. नहीं रे साइना इतना आंसर नहीं आएगा वही बोल रहा ना your I is constant, I is variable god. If your speed changes, your I will change. A constant नहीं है. You can't use V is equal to U plus AT and stuff. If your speed changes, EMF changes. If EMF changes, current changes. If current changes, again your speed changes. So you can't say A is constant. You can't write V is U plus AT. Try. I'll give 2-3 minutes. Always, you have to start like that. After time t, let the speed be V. Start from there. Give it a try. I'll just cut some water and come. So after time t, let the velocity be V. Magnetic field is this way. So V cross B, the battery will be like this. So the current will flow like this. So EMF will be BLV. Current I will be BLV by R. Now, if you draw the FPD of the rod, you have force mg. Now you have a current carrying rod in presence of a magnetic field. So current I is flowing with this IL cross B. So ILB will be in the upward direction. So here the magnetic force is dragging it. Acceleration. mg minus ILB is equal to ma. But I is BLV by R. This will be B square L square by R into V. This is nothing but dV by dt. If you look at this, this kind of looks like mg minus 6 pi r eta V is equal to ma, viscous force. Isn't it? Except for the constants, if you see, this exactly looks like viscous force. Dekho, mg minus 6 pi r eta V is equal to mass into acceleration, terminal velocity. So we call this thing magnetic drag. Then shift that side. So dV by mg minus b square L square V by R. It looks bad, but this is an integration which you guys can handle. Integrate on both sides. Speed will be 0 to V, 0 to T. This integration will be minus R by B square L square ln mg minus b square L square V by R. Limits will go from 0 to V is equal to T by M. So shift everything that side and put the limits here. This you'll end up with ln 1 minus b square L square V by mgr is equal to minus b square L square T by mr. Exponential, send it that way. So V is equal to mgr by b square L square into 1 minus e power minus b square L square T by mr. This velocity will exponential go there. And if you look at this term here, this is your terminal velocity. Isn't it? This looks exactly like viscous force. If you try to plot a VT graph, this velocity would increase and eventually become constant. Is this clear, everyone? Now, if the question is only to find terminal velocity, they didn't ask all this thing. You want to find only terminal velocity. So listen, there are one or two ways to do this. To just find V terminal. So when you reach V terminal, what will happen? At V terminal, acceleration is 0. That means the rod has reached a constant velocity. Mg is equal to ILB, A is equal to 0. We get mg is equal to ILB and I is equal to BLV by R. Substitute. Mg is equal to B square L square V by R. The terminal velocity will be mgr by B square L square. Bus. Make sense? There is another way to do. After reaching terminal velocity, resistor is there. This rod of mass M is falling with V, and this current I is flowing here. So, power lost by gravity. So, whatever energy you're losing in terms of gravity, speed is constant. So, kinetic energy is not increasing. Is nothing but heat produced in a resistor per second. That is the power produced in the resistor. So this is nothing but mgv is equal to I square R. Isn't it? Every second, whatever height you're losing, where is all this energy going? It should either go for your kinetic energy, but speed to nahi badh raha hai. So this energy is going somewhere else. Who can take it? Resistor. You can even argue like that. mgv is equal to I square R. You end up there, you'll get the same thing. I is equal to BLV by R. Substitute, you'll get the terminal velocity. But this is another way using energy method. The energy lost by the rod per second is the heat produced in the resistor per second. Make sense? But if you want as function of time t, there you have to integrate. And if you see, this is not really that different. Viscosity mein, when we derived, it was the exact same thing. Some constant into something into V is mass into velocity d. Here, this is the form P minus QV. The numbers are different. Mathematically, it is exactly the same thing. So Max won't care whether it's a magnetic drag or viscous drag. Clear with this? What if there is a capacitor? We change the equation. Now remove the resistor and put a capacitor. Now find the velocity as function of time t. Finish up. Last one for the day. Any doubts on this integration? Please ask me. This much integration you should be comfortable.
So when you took mg common, mg कहाँ गया वो? From the bottom step on the left to the top step on the right. So when you took mg common inside the lawn, वो mg कहाँ गया?
Did I take mg common?
What did you do?
That is a catch. I substituted limits record. Ln a minus ln b आएगा वो ln a by b.
Okay. mg divided.
And these people do big integrations in max. Physics people do innocent integrations. उसमें doubt है. हाँ. Max में they teach you all this monster Godzilla integrations तो कुछ problem नहीं आता है. Limits डालने में यहाँ पे people are having issues. Someone says मेरे आंसर log में आ रहे, मुझे समझ में नहीं आ रहा क्या करो. They don't know how to convert log into exponentials. No, I don't have a problem. If this was like 8 months back when your integration was not done, I could have totally understood your feelings. But after doing such monstrous integrations in your max and you're struggling with this, I will punch you guys. Capacitor का क्या करना gods? That was actually easy. Same story. After some time, let the velocity be v. Magnetic field is b. This will act like a battery EMF, which is equal to BLV. That means this will get a charge plus Q and minus Q. Therefore, charge on the capacitor is equal to C into EMF, which is BLC into V. Current in the capacitor or this wire is dQ by dt, which is nothing but BLC dV by dt, which is nothing but acceleration. Now draw the FBD of the rod. What are the forces? mg, ILB, acceleration. So mg minus ILB, which is BLCA into LB is equal to mass into acceleration. Interestingly, you get acceleration constant. Therefore, V is equal to 80. Play with this. When you put a capacitor, you get a constant current. And remember this question. We'll do this later on with an inductor. That is more fun. All clear with this? So put it down. We have done almost like 13 problems. In case you're doing EMI, I think you can start doing. If you're doing HCV, I think you can do first like 20-25 problems already. After next class, you will be able to do more. So next class, when we catch up, we will do something like, what happens if the rods start rotating? That is also fun. And then we'll do something called induced electric field. That would be the like pretty good one actually, that you can really ask good advanced questions on that. We will play with that. And after that, we'll have inductors and stuff that will kind of look like RC circuits only. So that will go pretty fast. But the main thing is an induced electric field. That is a little weird. Okay, so that will wrap up for the day. So next class when we catch up, we'll continue from here. So any doubts, anything, stay back and ask, or else you're free to leave. So take care, stay safe. I'll see you guys again next Wednesday.